All right, we're going to try a few word problems for solving quadratic equations. We're going to look at a few different ways to solve them, some efficient ways to solve them using all of those methods we've covered, and how we can check for valid solutions, if those answers make sense or not. So when we're given a word problem, we're looking at making a function, right? Usually in a word problem, we're not given the function, right? Or in a more complex word problem, we're not given the equation. We need to make that equation and then go ahead and solve it. That's what makes it trickier. If I have multiple variables, remember, I always need to solve basically x squared plus x plus, or let's call it ax squared plus bx plus c equals 0. I need to get to that point, right? And so I need to only have one variable. If I have two different parameters, so say length and width, right, or side 1 and side 2, and they're defined as different things, I want to make sure I can find a way to both define them as x so that I'm getting a single variable equation or a single variable function. Lastly, it's important that I make sure that I know if my answers are valid or not, right? Because when I get in context, yes, I know that every value exists in like the domain of a regular quadratic function, but in the real world, if a question is asking for integers or if a question is asking for length, there are values that don't fit those requirements that our quadratic might try to tell us are solutions. And those are called extraneous roots or extraneous solutions. So let's look at a few of these. So first example, which says example 2, ignore that. Length of a rectangle is 5 centimeters greater than twice its width. Its area is 33 centimeters squared. Find the dimensions. So they're telling me I know something about length, I know something about width, I know something about area, and what it's asking me, my final answer should be length equals this, width equals this, right? When I say find the dimensions, I say tell me those values. When in doubt, sketch it out. Let's draw a quick picture of what this rectangle could look like. It says the length is longer, right? It's 5 centimeters greater than twice its width. So what if I talk about both of these in terms of x? I can do some sort of substitution, right? But I can also set up the problem in some cases in one variable. So what if I just call my width x? Well, if my length is 5 centimeters greater, right, which means plus 5, than twice its width, then I can describe my length as 2x plus 5. So that way I know that length and width are different parameters, but I've already defined them both in terms of x, so that makes my life a little bit easier. So when I go to talk about the area of this function being length times width, well, I know the area is 33, and I know length and width both as expressions of x. So I can call length 2x plus 5, and I can call width just x. Now this is a quadratic function, and I can solve this. So one variable, I don't see any y's. However, when I am solving a quadratic, remember, I need to make it equal to 0. And this is not equal to 0. So just because these are factored doesn't mean these will tell me solutions because it's not equal to 0. So let's make it equal to 0 and then see, hey, can we factor? Should we use the quadratic formula? What's our best plan of approach? So I'm going to expand this out first. I'm going to say 33 is equal to 2x squared plus 5x. Then I'll bring everything to one side, 2x squared plus 5x minus 33. So now when I'm going to solve this, I could solve this graphically, which would be fine, right? It doesn't tell me to do it algebraically, so that would be a totally valid solution. I could do it by factoring, right? Now this one, it might not be obvious immediately that it is factorable, but there are numbers that multiply to negative 66 and add to 5. So that tells me I could go ahead and factor this thing. And then completing the square is always valid, but not very efficient, right? So realistically, unless I ask you to complete the square or it's already in vertex form, we're not going to use that method. Or we can use the quadratic formula, which is also valid. right? So lots of options here. I would say most efficient would either be graphically, because it doesn't say to solve it algebraically, right? If a question indicated, it doesn't say for any of these algebraically, but if it doesn't say, you can always solve graphically or at least verify graphically. Or by factoring, because it is factorable, right? We kind of want to stave the quadratic formula for situations where it's not factorable. So let's solve this one by factoring, because it is nice. So when I'm asking myself two numbers that multiply to -66 and add to 5, I get a -6 and a +11. So I have 2x squared minus 6x plus 11x minus 33. Take the GCF of these two groups, right? This is factoring by decomposition. There's lots of other methods you could use right here. GCF x minus 3 plus 11x minus 3. So I get a 2x plus 11, and I get an x minus 3. Now these two solutions, I can solve each of these for 0, right? Because it's equal to 0. I can use that zero product property, right? I can't do that here because this is not equal to 0. I don't have any rules about things that multiply to 33. So 2x plus 11 equals 0. 2x equals -11. X equals -11 over 2. X equals 3, right? Or if you wanted to see the work, x minus 3 equals 0, x equals 3. And so I have two options. Either, remember, what was x representing? X was representing my width. My width is either -11 over 2 centimeters, or it's 5 centimeters. One of these things does not make sense. This is an extraneous solution. My width can't be -5.5 centimeters. But if my width is 5 centimeters, then my length, I had an expression for it. It was 2 times that value plus another 5. So 15 centimeters. And I don't need to bother with the length for that 11 over 2 because it's negative, right? So the rectangle is 5 centimeters by 15 centimeters. And I just realized I did all that math with a 5 for no apparent reason. Let's try that again. So width is 3 centimeters. Length is 2 times 3 plus 5. Because I'm looking at my final dimensions, I'm like, that's not 33 centimeters squared. My length is 6 plus 5 is 11 centimeters. So my rectangle is 3 centimeters by 11 centimeters. That checks out, right? So think about there's a good test, a good example to make sure you're verifying, right, the reasonableness of your answers. Does it make sense? Have you actually answered the questions? All right, let's try another example. The hypotenuse of a right triangle is 10 meters. Hey, would you look at that? I'm going to start by drawing myself a nice right triangle. And I already know that this is 10 meters. One leg of the triangle is 2 meters longer than the other. When they say that, they're just referring to these two sides here, right? One side here versus another side here. One of these is going to be 2 meters longer. Well, that's already going to let me move this, already going to let me label the sides, because if I know that this is x meters long and this is x plus 2 meters long, then I have all three sides of the triangle. Now I need to think, what information do I know that compares all three sides of a right angle triangle? And that would be Pythagorean theorem, where side 1 is my a squared, side 2 or leg 2 is my b, and my hypotenuse has to be my c. That has to be my longest side. And so I have x squared plus x plus 2 squared equals 10 squared. Right? This is quadratic. I see x squareds. I do need to make it equal to 0, so I'm going to have to expand things. I know it feels silly to unfactor, to expand things that have already been factored, but unless it equals 0, it's not going to help us out. This is not really in vertex form because of the x out here, so I can't complete the square. So let's expand this. X squared plus, remind yourself that x plus 2 all squared is actually 2 brackets of x plus 2. And don't forget to square your 10 to get 100. So this is going to give me an x squared plus 2x plus another 2x plus 4. Again, that's just my full binomial expansion. Equals 100. Last but not least, I'm going to group all my like terms, bring everything all over to one side. And I'm going to call this 2x squared plus 4x minus 96. And now it's equal to 0. So let's bring it up over here. I can factor a 2 out. I can also divide everything by 2 because I have it equal to 0 here, right? Whoops. So let's look at it this way. Let's call it x squared plus 2x minus 48. And then see if maybe that's a little bit easier. This one is much easier to solve by factoring. So it'll be another good opportunity to solve by factoring. So I'm asking myself what two numbers add to 2 and multiply to negative 48. And the answer to that is a positive 8 and a negative 6. I can jump straight to those being my factors. X plus 8, x minus 6 equals 0. Solve these two now that it's zero product property. X equals negative 8. X equals positive 6, looking at the roots of that factored form, right? One of these things is extraneous. Because again, a triangle can't be negative 8 long on one side. However, it can be 6 long. And then that other side length, that x plus 2, is going to be 8 long. You'll recognize a lot of the time, because of kind of the symmetry of these parabolas, that your extraneous solute often looks suspiciously similar to your secondary solution. That's normal, that's fine, but make sure you're solving it appropriately and not just defaulting to using that value. So the length, the triangle sides are 6 meters, 8 meters, and 10 meters. And that gives us the sides of our triangle. All right, you're buying a new TV, a 42-inch TV. Ooh, wow. Now that is a big TV these days. And if you weren't aware, when you measure the length of a TV, they want to write the biggest number on the box, so they tell you the diagonal because that's going to be the longest side on the TV. So when it tells you it's 42 inches, that means the diagonal is 42 inches. Now I'm saying I have a width that is 16 inches longer than the height. So if this is my height, this is my height plus 16 more to give me my width. What are the dimensions of the screen to the nearest 1/10 of an inch? That's a sign that our answer probably won't be a whole number. So factoring might not be ideal, but we'll see once we start to look at our quadratic. I have another Pythagorean theorem situation. So h squared plus h plus 16 squared is going to be 42 squared. Right? Because those are the two side lengths, squared them, equal to the hypotenuse squared. I need to expand this out. This is going to give me h squared plus 32h plus, I don't know what 16 squared is off the top of my head, 256 is equal to 42 squared. I definitely don't know that one. 1764. There we go. And again, if you're not sure where this is coming from, I'm just making sure I do a full expansion of h plus 16 times another h plus 16, right? Which is h squared plus a 16h, whoops, plus another 16h plus 256, right? Well, we practice expanding these matching binomials a lot. So if you want to skip a step and say, hey, I know that this is just going to be double that inside, that whole perfect square trinomial, uncompleting the square, by all means. I need this thing to equal 0. 2h squared plus 32h minus 1508 is equal to 0. I can cut all this in half. I can divide everything here by 2. I can say h squared plus 16h minus 754 equals 0. But I don't know if this is factorable. I don't know if I want to spend the time thinking about factors of 754. So let's solve this one by quadratic formula. Because it's not nice to factor this. It's not easy. It's not immediately obvious. Right? I would hope that in a situation like this that we did up above, right, that this is easily factorable for you. Right? But even the first one, example 2, I could give you the benefit of the doubt and say you might not recognize that that's factorable. You might try using the quadratic formula because of that a value of 2, right? So just making sure we're choosing efficient methods, right? But using the tools that we have. So let's use the quadratic formula. So h is going to be equal to negative b plus or minus the square root of b squared minus 4ac all divided by 2a. And I'm calling it h just because I've called my variable h, right? That's what I'm solving for. Where in this case, a is 1, b is 16, and c is negative 754. So when I plug all those in, negative 16 plus or minus the square root of 16 squared minus 4 times 1 times negative 754. Whoops. All divided by 2 times 1. I'm going to simplify that discriminant value. I'm going to simplify what's underneath the radical. And I'm getting 3,272. Now I can keep this as an exact value and simplify that radical, but I'm seeing 1/10 of an inch, so that's my permission to actually evaluate this radical and get some exact values. I have 2 cases, one where I use the plus sign, one where I use the minus. So my first solution is negative 16 plus 3272 under the square root over 2. My second solution is 16 minus 3272 over 2. And what I can see from there, when I plug those into my calculator, is I'm going to get 2 different solutions. My positive case is going to give me 20.6006999 blah blah. My negative case, oops, lost my negative sign, is going to be negative 36.6, which again is extraneous. This is in inches. But as you know, as you saw in the last few examples, when I go to find that other equation, so here, h plus 16, I'm doing 20.6 plus 16 is going to be 36.6. The TV is 20.6 inches by 36.6 inches. All right, we'll do one more here. All right, so looking at this last one, a soccer player clears the ball from away from her goal area. The ball's path can be modeled by this function, negative 0.06x squared plus 3.168x minus 35.34. where x is her horizontal distance traveled in meters and h is the height in meters. So when we say in meters from the goal line, what we're assuming with that statement is that when I'm at x equals 0, that's my goal line. So we could solve this a few different ways. When I see those decimals, immediately I'm thinking factoring sounds awful. Completing the square sounds even worse. So really, the question is, do I want to solve this graphically? Oh, can I spell graphically? Or do I want to solve this using the quadratic formula? And it really comes down to questions like, does the question ask me to solve it algebraically, right? Or is the question looking for answers as exact values? Now, because everything's already in decimals, we're assuming that not. For the sake of getting some practice in, let's solve this graphically. Both of these are totally fine methods, but we just did use the quadratic formula. So let's solve this graphically. So I'm going to pull up the graph here on Desmos. Well, bam, magic, it's already there. And so what this allows us to see is this parabolic shape where it curves downward. We're seeing that at 0 is my goal line, right? Someone's running along the pitch. This is the moment where the ball gets kicked. This is the maximum height of the ball, right? The peak of its path. And then this is when the ball hits the ground again. Right, so making sure you know the steps to solve for these x-intercepts when you're using your TI or your Casio calculator software. All right, so I've taken a quick screenshot of our graph here. And so this is the goal line. This is where the kick happens. And this is where the ball lands. So when it's asking me how far away is the ball from the goal line when kicked, I'm looking for that first x-intercept. And so the answer here, 16.06, the ball is 16.06. Are we in meters? Yep, meters from the goal line. How far did she kick the ball? Well, what am I looking for here? I'm looking for this distance, right? I want to find the space between both of those x-intercepts. So what I'd like to know is I want to find land minus kick, right? So if it lands after 36.79 meters, but it was kicked at 16.01 meters, the distance between those two things is how long the ball was in the air for, right? Or how far the kick went. So when I do 36.79 minus 16.01, I get 20.78. The ball traveled 20.78 meters. Right, so keeping in mind the different strategies we have to solve quadratics, when it's efficient to use what, and how we can use those x-intercepts to solve different problems, right? What they mean when I model them using an equation I had to build, as well as using an equation given to me, right? So hope that was good. There is some examples in the textbook for you to give a try to practice some of those word problem and application problem type skills.